Hi everyone, today's lesson from Unit 6 is notes number 5, proportionality theorems. So we've used proportions with similar triangles, and today we'll look at how we can use proportions within a triangle or with parallel lines. Our first theorem for today is the triangle proportionality theorem, and it says if a line parallel to one side of a triangle intersects the other two sides, then it divides the other two sides proportionally. So what that means is that in our picture, line segment AC is parallel to DE. So notice those arrows marking them parallel. Then our takeaway from that is that we can write a proportion. And that proportion would be, we can compare the length of BD to the length of DA, and that would be equal to the length of BE over the length of EC. So as a proportion, we would get BD corresponds to DA in the same way that BE corresponds to EC. And because we have similar triangles here, due to the fact that we've got parallel lines, we have corresponding angles that are congruent. So we could also say, by the fact that we have similar triangles, we can compare line segment BD in this smaller triangle to line segment BA in the big triangle, and that would be equal to BE, this segment. That would correspond to this whole side, BC, in the same way that line segment DE, that's the third side in that small triangle, corresponds to line segment AC, the third side in the big triangle. The similar triangles, if you want to name them, would be triangle BDE, similar to triangle BAC. And again, they're similar by the angle-angle similarity. Okay, and our second theorem, it's the converse of the triangle proportionality theorem. So we're going to work in reverse with what we just did with our first theorem. And it says, if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So what we want to show is that if this line right here, DE, divides these two sides proportionally, then we can make this conclusion that the lines are parallel. So if BD corresponds to DA in the same way that BE corresponds to EC, then DE, line segment DE, will be parallel to line segment AC. So what we're going to do is throw those numbers into a proportion and see if it's true. So we want to compare 8 to 4. So that's the length of BD to the length of DA. And then we're going to set it equal to the length of BE, which is 12, divided by the length of EC, which is 6. And both of these ratios reduce to 2, so they are equal. So indeed, DE is parallel to AC. All right, our third and final theorem for today says if three, or it could be more, parallel lines intersect two transversals, then they divide the transversals proportionally. So I'm going to highlight the parallel lines N, J, and M, and notice that they intersect these two transversals. K is a transversal, and line L is a transversal. So if we know for sure that line N is parallel to line J, which is parallel to line M, which is kind of a funny way to write it, but if all three of those lines are parallel, then we can say for sure that the length of AB, right here, compares to the length of BC right here. So we're going to compare those two. And that would have to be equal to the length of DE divided by the length of EF right here. So I'm going to erase those marks and put in some numbers for us to take a look at. Okay, so our given information is still true. The lines are parallel. And so now let's check it out. If those three lines are parallel, let's say if this is 4 and this is 2 and this is 3, then we have to solve for x right here. So what we'd want to do is set up 4 over 2 and then set it equal to 3 over x. We'll cross multiply and get 4x is equal to 6, because 3 times 2 along that other diagonal is 6. Take and divide by 4, and you end up with x is equal to 1.5. Okay, so next we are going to put those theorems into action. In our first example, we're asked to find the length of AB. So this segment right here is AB, so I'll assign it a variable so we can solve for it. So the one thing we have to check for is to make sure our segments are parallel. So AE and BD are definitely parallel to each other. So we're going to use the triangle proportionality theorem. So since those lines are parallel, we can compare the length of this segment BC to AB. So that will give us 3 over x. And then that would have to be equal to the length of this segment, 4, divided by 12. Now you could reduce first if you chose to, but we can go ahead and just cross multiply. 4 times x is 4x, and that's going to be set equal to what we get along the other diagonal. 3 times 12 is 36. Take and divide by 4 on both sides, and we get x equals 9. Final answer. Just want to point out one thing. I set up the proportion going one way, but you could also have set up the proportion x over 3 is equal to 12 over 4, and you'd still have the same result. 4x equals 36, and it would give you x equals 9. Okay, number 2, we have a different type of question. We have to determine whether our two line segments are parallel. So we have to figure out if SY is parallel to EL. So what we want to do in this case is actually set up a proportion where we compare 18 to 10. And we see whether it's equal to 24 divided by 15. So again, watch for that pattern. Notice I'm going from this side in the triangle to this side in the larger triangle, that piece of the larger triangle. All right, I would probably just reduce these two fractions, and 18 over 10, if I divide by 2 in both the numerator and the denominator, I get 9 over 5. And 24 over 15, I know that I can reduce it by dividing by 3. 24 divided by 3 is 8. 15 divided by 3 is 5. Well, if we check out what we have 9 over 5, or 9/5, equal to 8/5. Well, that's not true. They're not equal. So we can say for sure that line segment SY is not parallel to EL. So again, they are not parallel segments. In order for them to be parallel, those ratios have to be congruent. Right, for our last example, it says, for the figure below, which statement is not true? So be careful. We're looking for something that does not work. So in the first answer, it says KL corresponds to LM. So I'm going to highlight as we go through here. So it says KL corresponds to LM. So we're comparing those two in the same way that PO corresponds to ON. And that one is actually true. So we're going to hold off and try another one here. So I'm going to erase those marks. Choose a different color here. Right, in part B, it says that ON corresponds to PO. So here's ON, and it's going to correspond to PO. Alright, so that's our first ratio. So our second one has to follow that same order. And notice that it compares LM to KL. So this one is also true. Alright, our third option here is a little bit tricky. So in this option, they say they're comparing LM to MN. And they're saying that that would be equal to ON over MN. This is the one that is false. In all of the proportionality theorems, we never use this segment in the middle. Okay, so this one would definitely be false, but what we should do next is follow through and take a look at the last answer choice. In the last one, notice that it compares KL, this piece, to KM, the whole segment. And then with the other fraction, it compares PO to PN. Right? In this particular case, it would be true, because you're comparing part to whole on the two sides. You can try testing this out, testing all 4 scenarios out if you put in numbers. But you gotta be careful about the numbers that you put in. For example, we have to make sure that this number, this segment compared to this segment, is equal to the ratio of this segment over this segment. So you can see I've chosen some numbers where 6 divided by 3 is 2, 4 divided by 2 is 2. And then let's just say that this length in the middle is 1. Well, that would help you confirm that choice C is false, because that would give you 3 over 1 equal to 2 over 1. And they're not equal to each other, so again, that's why it's false. If you plug those numbers into all of your other ratios, you would confirm that A, B, and D are all true. Alright, good luck on homework number 5. As always, make sure you see me for extra help if you need assistance with the homework.